In studying these diagrams, it is essential to note the location of the source of input to each device. That is, the CTs and the VTs. Of course, here we are looking at a one-line diagram. Here is part of a typical three-line diagram showing more detailed connections. Another type of diagram that you must be completely familiar with is the control circuit schematic. As we've already mentioned, circuit breaker components may be physically far apart. The closing and tripping coils are located adjacent to the breaker. The manual switching contact considerable distance on the control panel. The protection relay contacts inside the relay may be in yet another location. However, from an electrical point of view, the breaker control circuit looks like this. The DC positive and negative may be drawn horizontally or vertically. It really makes no difference. You soon get used to working through the circuit to determine the sequence of events. Look at the closing circuit of this breaker. To energize the closing coil, the circuit must be completed by closing one or more of these pairs of contacts. This symbol indicates an open pair of contacts. Do not confuse this with the symbol for a capacitor, which looks like this. Now, a closed pair of contacts is shown by this symbol, and indeed, if they are closed under normal operating conditions, the letters NC may be added. Similarly, NO means normally open contacts. Conventionally, the diagram is shown with the contacts in the at-rest condition. That is, the tripping and closing circuits are de-energized. The circuit breaker is open. You would think that to close the breaker, it would be sufficient to close any pair of the manual switching contacts. In this installation, we have local and remote operation. But look, there are other contacts in series with the closing coil, and these are known as permissive contacts. For example, this pair will only close when there is adequate pneumatic pressure available to operate the breaker mechanism. This pair of permissive contacts are only closed when a synchronizing relay determines that conditions are correct for closing. And yet another pair only close when there is no remote inter-tripping signal on the system. I'm sure you can think of a lot more permissive conditions. Once all of these permissive conditions are met and all contacts closed, the breaker will close when you operate one of the closing switches. On most breakers, once closed, both the closing and tripping circuits remain de-energized as the mechanism is mechanically latched in. How is this achieved? When the breaker is firmly closed, it mechanically actuates auxiliary contacts in the control circuit. It opens the auxiliary contacts here, de-energizing the closing circuit. At the same time, it will close these auxiliary contacts in the tripping circuit, so enabling this circuit to operate when required. To trip the breaker open, the tripping circuit must be energized. In the case of a tripping circuit, instead of permissive contacts in series, we'll find several pairs of contacts in parallel. Look at these tripping contacts: overcurrent relay, manual switching, differential relay, remote intertrip. Closing any one of these pairs will energize the tripping circuit and open the circuit breaker. Often these tripping contacts are provided with seal-in circuits, as we discussed in the previous segment. We have been looking at a relatively simple control schematic. In practice, these diagrams can become quite complex. You'll find it most challenging to get hold of a set of control diagrams on your own job and work through them. In fact, I'll leave you with that as an exercise. Let's take a break. At zone protection. Please switch off the tape and go through this material in your workbook. In our typical power system, we have generators, including their step-up transformers, buses, transformers, transmission lines, sub-transmission lines, distribution lines, and utilization equipment such as motors and static loads. Also, on most systems, capacitor banks and reactor banks are installed. Now, all of this equipment needs to be protected, but the type of protection used is generally different for each area. So it is convenient to apply the protection to distinct zones. For example, let's start at the generator zone, which includes its associated step-up transformer. Any fault within this zone would result in tripping of the main generator breaker here, and hence isolation from the power system. This will protect against faults in 1, the generator itself, 2, the primary of the transformer, 3, the secondary of the transformer, and 4, the breaker. The next area of protection is the bus zone. The bus will normally have several incoming and outgoing connections. After all, that is the purpose of the bus. Any fault on the bus requires that all breakers, incoming and outgoing, must be opened. So typically the bus zone area will overlap the generator area like this. You can see that these generator breakers will operate either for a fault within the generator zone or a fault in the bus zone. The next area in this particular power system is the transmission line zone, and once again, this overlaps the bus zone at either end. Hence, these breakers will open for a line fault and also for a fault on its respective bus. In this particular substation, we have a transformer which reduces voltage down to distribution level and feeds the distribution bus. So we have a transformer protection zone, and this overlaps the bus zone on either side. On many systems, a sub-transmission line zone would be installed between the transmission and distribution systems. In this example, the distribution line feeds a particular industrial customer who has installed large motor loads. So we have further zones of protection. Here is the distribution line zone overlapping the distribution bus zone, and at the other end overlapping the motor protection zone. Now remember, we're not talking about the type of protective relays installed, only the zones of protection. In each zone, primary protection is installed to protect the equipment within that zone. In addition to this, backup protection is provided from other relays or from duplicate relays. It is no coincidence that as we go through this video training program, we'll be looking at each of these zones in great detail, studying the types of relays, protective schemes, and configurations employed in current practice. Looking at the list of videotapes, you will see generator protection, transformer, reactor, and capacitor protection, bus protection, motor protection, line protection, that is, transmission, sub-transmission, and distribution, pilot protection, system stability, including reclosing and load shedding. But before we get into that, we'll have to study in the first tapes some of the basic technology and fundamentals to help us understand what happens to the power system under fault conditions. Up to now, we've been talking about protective relays. In fact,